The universe is expanding. This is a well-established fact and one that scientists have known for nearly a century. It was first proposed by Russian physicist Alexander Friedmann in 1922 and again independently in 1927 by Belgian astronomer Georges Lemaitre. Confirming observational evidence was first published in 1929 by American astronomer Edwin Hubble. While the expansion of the cosmos is accepted nearly universally among the scientific community, two very precise estimates of the rate at which the universe is expanding disagree with one another. This is called the Hubble Tension, and it may be the first significant inkling that cosmologists have overlooked something in their theory of the creation and evolution of the universe. While the explanation of the disagreement might be ascribed to an error in one or both of the estimates, recent measurements suggest that the discrepancy is real, leaving scientists to take a hard look at the entire situation. Universe expansion. A rubber band analogy. The expansion rate of the universe can be a confusing concept that is perhaps best introduced by analogy. Suppose you have a rubber band that is 2 units long, with a mark at the center. You attach one end of the band to an unmovable hook and hold up the other end to ensure that it is straight. Thus, the end you are holding is 2 units away from the hook, while the mark is 1 unit away. Then, imagine that you grab the loose end and stretch it, so as to double the length, taking 1 second to do it. The end is now 4 units away from the hook, while the mark at the center is 2 units away. Thus, the mark moved 1 unit in 1 second, while the loose end moved 2 units in a second. The key point is that the spot more distant from the hook moved more quickly than the one nearer the hook. In the language of cosmology, the velocity of a spot on the rubber band is 1 unit per second for every unit of distance from the hook. The expansion of the cosmos is exactly the same. More distant objects in the universe are moving away from the Earth quicker than closer ones. In round numbers, distant galaxies move away from the Earth at a rate of 70 kilometers per second for every million parsecs of distance. A parsec is a historical unit of astronomical distance equal to 3.26 light years. Thus, a galaxy at 1 megaparsec from the Earth moves away at a rate of 70 kilometers per second. A galaxy 2 megaparsecs away moves at a rate of 140 kilometers per second. This rate is called the Hubble constant, and the basic idea is very well established. The Hubble tension. However, there are several ways to determine the Hubble constant. The first and most straightforward way is to measure the distances to galaxies and simultaneously measure their velocity. You can then determine the galaxies' velocities as a function of distance. When you do this, you find that the Hubble constant has a value of about 73 plus or minus 1 kilometer per second per megaparsec. Different groups obtain slightly different values, but they are all quite consistent. This value of the Hubble constant is called the late-time version, as it is determined from the period relatively late in the lifetime of the universe. There is another way to determine the Hubble constant by examining the conditions of the cosmos shortly after it began. The universe began 13.8 billion years ago in a cosmic cataclysm called the Big Bang. While it is somewhat misleading, one can imagine the Big Bang as a vast explosion, which included a glowing fireball and a rumbling sound. In the very early universe, the fireball was impenetrable, but when the cosmos was a mere 0.003% its current age, the expansion cooled the universe enough that light could escape the fireball and travel across the cosmos. While the universe was glowing hot at that early time, the expansion of space over the eons has cooled it until the light is no longer visible. Indeed, that once visible light is now only microwaves, which can be detected by radio antennas. This primordial whispering remnant of the Big Bang is called the cosmic microwave background, CMB, and it was first detected back in 1964. The sound waves of the Big Bang were locked into the early fireball, resulting in tiny variations in the CMB. Astronomers can measure those variations very precisely. Using those patterns, they can take all factors known to have any relevance to the Big Bang and subsequent evolution of the universe and predict a value of the Hubble constant for our current day. This approach hinges crucially on the measurements of these variations in the CMB as well as various theoretical ideas. Using this early time information, astrophysicists predict that the Hubble constant should be about 67.5 plus or minus 0.5 kilometers per second per megaparsec. And there's the rub, as they say. The early time and late time measurements simply disagree, and this specifically is what is referred to as the Hubble tension. Disagreements tend to generate excitement in the astronomical community because a discrepancy of this magnitude could mean theories need to be rethought. In other words, there is more science out there to discover. What explains the Hubble tension? However, before anyone gets too excited, it is important that researchers verify their results. A mistake in a measurement could explain everything. The most likely mistake is that researchers determining the late time value of the Hubble constant could have mismeasured the distance to the galaxies they have studied. However, two new studies claim to have reduced the range of possible uncertainties of late time measurements to such a degree that many researchers are beginning to think about how our understanding of the birth and evolution of the universe might be modified. So, what could it be? The early time measurements predict that the Hubble constant in the modern day should be smaller than is currently measured. If taken seriously, this implies that some unknown physical phenomenon gave the universe a kick early on, resulting in the current, speedier measurements. One idea that has been proposed is that during the first 10% of the lifetime of the universe, a form of repulsive gravity turned on briefly, giving the expansion of the universe a brief nudge, before somehow turning off and disappearing. While that conjecture is certainly a bold one, it is similar to a phenomenon we see in the current day, in which a form of energy called dark energy is causing the expansion of the universe to speed up. Since we observe strong evidence for dark energy, suggesting a similar effect earlier in the history of the cosmos isn't unreasonable. Regardless of the final explanation, the Hubble tension is shaping up to be a fine mystery. Ongoing efforts continue to try to refine both the early and late time estimates of the Hubble constant. And it will be some time before the question is resolved.